Thank you very much, Jan. Good morning, everybody. It's great to see so many people here present at this event, and I'm also very honored to be able to present some of my work here today. I'm very much aware that I'm totally preaching to the converted when I tell you that we know more about the face of the Moon and the face of Mars than about our own deep oceans. However, it's a cliche, but it's unfortunately true. NASA has mapped Mars to a pixel resolution of about 100 meters, while the latest estimates have indicated that for our oceans, only between 5 to 9% of the seafloor has been mapped to that resolution or any better. At the same time, the Census of Marine Life program between 2000 and 2010 established that we still discover or describe more than 1,500 new species every year, and that includes big species, squid, fish. A few years ago, we even had a new species of whale. At the same time, they also estimated that we only know about a quarter of the species in the ocean. And if we even don't know what lives there, how can we ever estimate how it functions? I also know that you're very much aware that the human impact in the ocean is expanding rapidly. We are extracting oil and gas, fisheries. A lot has been said recently about the extent of human litter in the ocean. And so I know that you all agree that there is an urgent need for a better understanding of our oceans if we ever want to be able to manage this massive resource in a sustainable way. And if we are working towards marine spatial management, the first thing people generally ask for is a habitat map. If we take this definition of marine habitats by Harris and Baker, then you'll understand that a marine habitat map is a very good summary document of the characteristics of your marine environment. And to create it is an inherently multidisciplinary activity. We have to gather information about the abiotic or physical environment, combine that with biological data, and in most cases the biological data is only known at specific point locations, while the environmental data is more often known as a spatially continuous data set. So we use the environmental data to predict where certain species occur, or at least we classify the environmental data to know which different types of habitats we might have in the ocean, and we then try to combine that with the biological species or communities that might occur there. And throughout this whole process of marine habitat mapping, the National Oceanography Centre in Southampton has a lot of expertise. So as Jan said, I'm based at the NOC in Southampton, which is one of the 6 research centres of the Natural Environment Research Council. Although I have to say, on the 1st of April, we will be transferred to a new overarching research council called UK Research and Innovation. And the NOC is home to a whole list of facilities that will help marine researchers within the UK, not least the research vessels, the Marine Robotics Innovation Centre, the Marine Equipment School, the Data Centre, Oceanographic Library, and also the core store facility. NOC has 480 NERC staff, many of them related to the ships and the facilities, but we are also 160 scientists and engineers working towards research and development. The site is shared with the University of Southampton, so we also very closely collaborate with them for the science and to develop new master's and PhD projects. And as I said, we have a long-standing expertise in seafloor and habitat mapping. In all of the aspects of the whole procedure to create the habitat map, so that includes data acquisition, both the environmental and the biological data, processing of those types of data sets, developing new software and approaches. The top-down approach to habitat mapping, so starting from the environmental data, classifying that in different habitats, and then identifying who lives there. Again, we develop our own techniques and approaches. We also have expertise in the bottom-up approach, predictive modeling. And then as the 5th pillar of our marine habitat mapping, we also have a very close relation to marine policy, and I apologize for all the acronyms here. Those are mainly the names of different UK governments departments that are related to the marine spatial planning process. Our habitat mapping work occurs in a whole range of environments, many deep water environments, but also coastal environments, and specifically vertical communities, which is one of my main interests, and we will come back to that later. So just in the next 5 or 10 minutes, I'll give you a few examples of the type of habitat maps and habitat mapping work we do. And I will start off with a top-down example from South Georgia. In 2014, the biggest marine protected area on the planet at that time was designated around South Georgia. But actually the South Georgian government did not know very much about the seabed environment and the different habitats present. And so we used, as I said, the environmental data, classified that in a statistically robust and objective way to identify the main marine landscapes in the area. And even at this stage, we did not correlate with biology data. Just knowing how heterogeneous certain areas are and how homogeneous other areas are helps the government with their marine spatial planning. So we communicated that directly to the South Georgian government. The other thing we managed to do was to estimate the confidence on our habitat map, which again would help the government in making decisions. And now we're at the second step, combining with biological data, and for South Georgia that's actually fantastic. There is about 130 years of species records available for the area. They're held at the British Antarctic Survey, VLIZ. And so we looked at those species records and did some cluster analysis to see if those species would fall apart in communities that would identify our different marine habitats or our different marine landscapes. And as you can see, our first attempts were rather frustrating. But you can also see that the spatial distribution of the sample points is not ideal. There are a lot of samples on the shelf and on the upper slope, and not very many in the deeper waters. So once we managed to account for all of that, we actually did find that our different marine landscapes have specific ecological communities. The second example is a bottom-up example, where we did habitat suitability modeling in the Whittier Canyon, which is one of the major canyon systems in the Bay of Biscay. We collected bathymetry data there, and also a series of ROV video transects, 14 video transects spread across the easternmost and westernmost branch of that canyon. And our PhD student, Kathleen Robert, did a number of suitability modeling attempts. Generally, she had to model summary parameters such as abundance and diversity rather than specific communities, because with 14 video transects spread over a 200-kilometer long canyon, you don't get very far. The diversity map that I can show here, and unfortunately the red colors are gone, but you can still see that the highest diversities are predicted in areas with the highest heterogeneity and the steepest slopes. So the map does make sense. Unfortunately, the statistics told us that only 23% of the diversity was explained by our model. And the reasons for this relatively low number are related to scale. As I said, we had very limited sampling, but also there are several patterns and processes that we have not accounted for, and many of those happen at a scale between what we see in the picture, which is 1 by 1 meter, and the bathymetry from the ship, which has pixel sizes in the order of 50 by 50 meters. In addition, that shipboard bathymetry did not give us a very good 3D terrain information. It tends to smoothen the terrain, not accounting for real steep slopes. The solution to those problems, we think, lies in the use of marine autonomous and robotic systems. And this picture was taken in 2014, I think, and illustrated the state of our robotic fleet at that moment. So at the front you can see a whole fleet of gliders. The larger yellow vehicles are the AUVs, the AutoSub series. We also have a workhorse ROV, remotely operated vehicle, and then we have a series of surface vehicles as well. And in 2015, we took 3 of those vehicles into the Whitworth Canyon, and that was actually the first UK science expedition where we deployed 3 different robotics simultaneously working together in that submarine canyon. At the same time, we had colleagues on the Celtic Shelf, 3 different colleagues who were also deploying different robotics. So we had 6 vehicles in the water in more or less the same region, which was quite exciting. Just a bit more information about those main vehicles. So AutoSub 6000 is the deepest diving AUV of the AutoSub series. It goes down to 6,000 meters and stay underwater for 24 to 28 hours, depending on the equipment used and battery power data. We mainly use it for terrain mapping using echo sounders, but it can also do photography in terrain that's not too irregular, because it needs to stay about 3 meters above the seabed to do that. But it can take 1 picture every second. If you stay underwater for 24 hours doing that, you can calculate how many pictures that creates for one dive. The other good thing about the AutoSub series is that the engineers have designed the AutoSubs in such a way that once they're confident that the AUV has started the mission correctly, it's an autonomous vehicle, so it stays on its own and we go off and do something else. And so that's our solution to the limited amount of data. We have actually 2 vehicles doing the data collection at the same time. The second vehicle we work with a lot is the ROV ISIS. Also full ocean depth, equipped with high definition video and high resolution photography. It can do precision sampling with its 2 7-function arms. And we also sometimes use it for ultra high resolution bathymetry mapping. And then the third vehicle at that time we had in the water was a vehicle from the University of East Anglia, but in the fleet that I just showed you we have some similar vehicles. And that's a sea glider that can dive down to maximum 1,000 meters depth and keeps making profiles up and down. It did that for 21 days consecutively, and it measured temperature, salinity, oxygen, and turbidity. So using these tools, we can actually cover all the scales and the depth ranges that are necessary. So we kind of make a nested map. In the background, you see the bathymetry that comes from the shipboard multi-view system. And in the center, you see the bathymetry from the AutoSub, from the AUV. Zooming in on this particular spur, we also had ROV bathymetry with a 10 centimeter pixel size. And then you can see those little lumps or moundy features, which turned out to be cold-water coral reefs. Using the high-definition video, we can then zoom into to the level of individual polyps and individual gastropods. So using this nested approach, we really can image seafloor processes at the scale they occur and understand the connections between those scales and processes. And working at the scale that actually is appropriate for your question is very well illustrated by the work we did on some of the hydrothermal vents in the Southern Ocean, the southernmost hydrothermal vents ever discovered in the planet. Hydrothermal vents, by their nature, are extremely localized habitats or ecosystems, and so at that moment it's the best way to map out the different assemblages of communities is by making a massive photomosaic, because some of those vents are meters to tens of meters high, and then doing the mapping from that. And this is informational data that was, or a paper that was published in 2012, and Lee Marsh, at that time PhD student, spent a couple of months painstakingly stitching photographs together. Computer vision software and technology has advanced so much nowadays that we can all do this automatically. And nowadays we use a technique called Structure-from-motion, which is a photogrammetry technique where a series of pictures, overlapping pictures taken by one camera that moves, can be stitched together and create a full 3D model of your terrain. And we use that, for example, to map out that small cold-water coral reef. So the reef is about 15 to 20 meters across and about 5 meters high. And this gives us an idea of the reef structure. In the deep sea, you can never see a reef in its entirety because you can never have the lighting correct to see the whole reef at once. But at the same time, the 3D model also allows us to derive characteristics such as slope, aspect, rugosity, and other terrain variables that help us understand the niche partitioning between individual species and individual specimens. As I said, the shipboard bathymetry also tends to smoothen out vertical or very steep terrain, and so we developed a method to get around that as well. Again, in the Whittier Canyon, on the shipboard bathymetric profile, we saw that some of the flanks were really, really steep. And so we worked together with our engineers to change the position of the multi-beam echo sounder, which normally looks downward from the ROV. We placed it on the front of the ROV, and then we moved parallel to the vertical terrain in order to create a map of the morphology of that cliff. We did that at several stages, starting off quite far away from the cliff, safety precautions, and then gradually coming in closer. And staying far away, of course, we have a bit bigger overview of the entire cliff. And so you can see that actually the colors indicate the distance between the cliff and a vertical reference plane. And you can see that actually the cliff is overhanging, so you would never be able to map that from a downward-looking ship multi-beam anyway. You can also see the geological structure of the cliff. It's about 120 meters high, and on the map we could see it was about 1.5 kilometers long. Moving in closer, we can then see every single bedding plane, and also these lumps, which turned out to be coldwater coral colonies, so the entire cliff is a fantastic reef, which protects itself to bottom trawling by the sheer fact that it's vertical. The same technique can also be used, for example, for geohazard research. This is an example of where we did vertical mapping on the vertical headwall scarp of a submarine landslide to help people who do geomechanical studies of sediment packages to understand better the structure of the package that has failed. And then as a last step, again, striving towards bigger efficiency, trying to do several things at the same time, we again worked with our engineers, this time the AUV team, in order to be able to also map those cliffs with AUV. In this case, we were turning the multi-beam system sideways. The biggest challenge for the engineer was not so much tilting that multi-beam system. It was the development of a cliff tracking, so that the distance of the AUV to the cliff would stay the same, and also collision avoidance in case there would be some part of the cliff sticking out. And so this is just a quick representation of the results. So this is a point cloud model. So the sparse points in the background show us the data that we normally get from a shipboard multi-beam. And you can see that's much less data points than what we get with vehicles when they get closer to the seabed. Then this cloud is what we got from the AOV, and then nested in there again we have an ROV forward-looking multi-beam set, which beautifully illustrates the geology of the area. And then again we can correlate that very well with the photography, identifying the niches of all these individual species. And so Kathleen Robert has actually worked that up, has studied the biology of vertical communities in different locations west of the UK and Ireland, and she has found that yes, different vertical cliffs have different communities. They're generally quite rich, but also within individual communities you can find a niche separation between species. So that's kind of a whirlwind tour through what I've been up to in the last 10 years or so. I was also asked to tell you a bit about my career and how I got involved in all of this. My first degree is actually environmental engineering, or bioengineering as they call it here in Belgium, which I got here in Ghent University. And I was focused on land and forest management, so a lot of spatial analysis, a lot of GIS. And I will admit the engineering, even if it's not mechanical engineering or electronic engineering, does help with all the technology that we've been using. After that, I decided to take 1 year to study something that I found interesting. No worries about employability or anything, just something I found really interesting, and I wanted it to be abroad, to have the abroad experience. I did not have the chance to go on an Erasmus exchange, so I took an extra year abroad, and that was the Masters in Oceanography at the University of Southampton. From that moment, my path was set into the marine direction, and so I came back again to do a PhD in marine geology, studying giant cold water coral mounds. So that's when I got into the cold water coral research, and again using a spatial approach to that. After that, I did a series of postdocs, kind of ping-ponging between Ghent and Southampton. And after a first year in a research and training network, I wrote my own Marie Curie fellowship. And I have to admit, that has been a really, really good experience. It really gave me the opportunity to take project ownership, to write the proposal myself, to manage it, to manage the budget, to make sure all the deliverables were there. The other thing I have to say is that many of my positions, actually all of them, somehow were related to European projects, so that gave me fantastic opportunities to create a strong network. Marine research, you never do alone. After the Marie Curie postdoc, I was very lucky that I received a permanent position at the NOC. And so since then I've been participating in a lot of European and national projects. I've also participated in a lot of cruises. Since the beginning of my PhD, I've spent the equivalent of more than 2 years at sea. And during those cruises, I very often acted as the scientific liaison between the engineers and the scientists. I've been on several trials cruises where they try out new equipment, giving the scientific side of things, telling them what scientists would need from the technology. Following that, I also attracted a starting grant from the European Research Council for the project CodeMap, and you've seen some of the CodeMap results throughout this presentation. I really have to say also that one empowered my career. I had the chance to build a research team to attract my own PhD students, postdocs, to start the InSize network for submarine canyon research, and to act as chief scientist on some of those big cruises. That project finished last year, but in the meantime we're already forming new projects, again developing new habitat mapping techniques and also applying habitat mapping in developing countries. So I was also asked to give some career advice for young marine scientists. First thing I could advise you is collaborate. The oceans are far too large to do it all yourself. If you work together with people, you can bounce off ideas, you generally create more knowledge and more exciting new possibilities, innovations. And if you're of the calculating nature, if you work together, you'll actually share, but also join other people's papers. It does help your publication record. Collaborate outside your discipline and outside your comfort zone. The ocean is so complex, and it's only multidisciplinary approaches that can help us to really understand how the ocean works. However, if I say multidisciplinary, I don't say that you have to do it all. Find your niche, become a specialist in 1 or 2 subjects, and learn about all the others. Keep learning all the time, but learn about the others through your collaborations. So, for example, in my case, I know a lot about cold water corals and submarine canyons, but what I really know about is habitat mapping and the use of deep submergent vehicles. Don't be afraid of new technology. I guess this presentation oozed all of that. Get involved, and as I said, get involved in a dialogue. You don't have to be the engineer, but if you can tell them what you need, it makes it so much more interesting for them to develop the new technology. Because otherwise they will just develop something because it's cool, because they think that this new thing they can do. If you say what you want to measure, they will be very happy to try to make that for you. And finally, I would say, work towards delivering quality science, but quality science with relevance. The examples I've been giving, there's a lot of application of habitat mapping for marine spatial planning, also the geohazards work, for example. It will give you a much bigger reward if what you work towards also has relevance for the community. I then also have a few bits of career advice for the not-so-young marine scientists. I don't know if there are many in the room, but for those of you who are here, I would say please support your students and early career researchers as much as you can. I've had, throughout my career, a number of fantastic line managers, and if they wouldn't have helped me the way they did, I would not have been able to do the Marie Curie and the ERC. So give your students and early career researchers all the opportunities you can. Give them a few challenges as well. I've been thrown in the deep end a couple of times, but generally it helps you to learn a lot very quickly. Also, for not so young marine scientists, collaborate. Collaborate with young scientists, and don't be afraid of the technology they bring. It will help your research forward as well. With all of that, I have a massive list of people to thank, and I'm pretty sure I might have forgotten a few. And also all the people on board of all the cruises where I managed to collect the data. Thank you.